Hello and welcome to today's webinar. Glad that you're here with us today. Just like in every other webinar that you've probably been in, mics will be muted. You can certainly ask any questions or have any comments that you might have in the chat function down below. And we can go ahead and jump right in to today's topic. But first, just want to say thanks again for joining us. I know your time is valuable, and so we hope you get some good knowledge out of today's presentation and something that will be very useful for you in the future. So my name is David Cash. I am a member of the marketing team here at Mountz. I've been with the company for nearly 16 years now, and in the torque industry for just about over 20 years now. And with Mountz was founded in 1965. We've been a torque company ever since. We were the first torque company to develop the electronic torque tester. Since then, we've had 18 different generations of torque analyzers. We have our two facilities, one our headquarters in San Jose, California, and also our warehouse, distribution, and Eastern Service Center in Foley, Alabama. So as we get into today's topic of error proofing with CAM technology, let's take a look at the process that we're all trying to achieve with torque control. And that is kind of the name of the game as it relates. We want to keep parts that are meant to be together, remaining together without any type of failure in that. And so I guess a lot of the risks that come with fasteners that can go wrong is they can break and due to over tightening. You've got a lot of costs in rework. Also, if there's line shutdown or delays as far as being able to produce your products, and then also there are human errors that we have to engage with too as part of the risks dealing with torque control. So as we look at is your application critical? Well, if we take a look at the torque that is around us every day, we can see that the torque is very, very critical. From when we're out traveling, trying to get from one place to another via airplanes, we want to make sure that those are put together. Satellite communication, everything from the cars that we drive. If you're traveling down the highway at a very fast rate of speed and something goes wrong that way, that could be very dangerous as well. Now, cell phones may be critical for teenagers, but also we want to be able to protect the ones that we love, and we want to make sure that everything is tightened correctly. Now, there are some hypercritical applications as well. If we take a look at this particular laparoscopic surgery robot, we certainly do not want to have any type of torque failure as it relates to any type of medical or even military or ammunitions, things like that as it relates to some of the hyper critical types of applications. So we want to make sure that we can provide error proofing solutions for those particular applications. And we can do that with the use of CamOver technology. So when we look at hand tools in general, what is really going to separate one hand tool from another, even though they may fall under the same umbrella as a certain standard, but it's all going to come down to the torque mechanisms that are built within the tools themselves. So when we look at torque screwdrivers, also torque wrenches, the main thing that's going to differentiate one tool from the next is going to be its torquing mechanisms and the clutch in there that is going to help to deliver the proper torque that is needed. So if we look at here on the demo bench. And so if we take a look at how these particular tools work when they reach torque value, they have a different type of clutch than we would that we have. So we'll take a look at the clutch mechanism in this tool first. And so if we go ahead and remove the cap here, so you can see here that the ball bearings that are used in this particular tool for its clutch mechanism is right here. Let me just zoom in here real quick. So in the most cases of a lot of the torque screwdrivers, primarily we're using spring to be able to provide us the repeatable torque value that we're looking for. And so as this tool clutches, you can see it has 4 different lobes in here, and the ball bearings sit inside of these particular lobes. And then we have a torque arm right here, where these particular ball bearings will go up and over. So as torque is achieved, the screwdriver will hop over those particular ball bearings, and that's how torque is achieved with this particular clutch. So again, as torque is going, the spring gets compressed, then the tool will simply hop over the ball bearings here and then move into the next lobe that it would be using for its torque delivery system. So with that tool, that is what we would be looking at. This tool uses a very similar so the clutch here is primarily the same type of function. We have 3 ball bearings that will sit in this clutch, and with this holder, and then the ball bearings will again hop into the next divot or next location for its value when it has achieved torque. So again, as the spring is compressed, the ball bearings will then force the tool up and over, and then it will come back down again to be into the next lobe, up and over. So we see a vertical type of torque delivery as the tool goes up and then goes down for this particular style of tool. So make sure we capture those. So those are a couple examples of some clutch mechanisms and how those two differ, and then also how they are going to differ from the Mountz product that we have. So with our torque delivery system in our torque screwdrivers, we use a cam mechanism to do that. This is going to help us give us that error proofing CamOver effect that we have. It's not going to allow for any additional over torque that's happening. We get a nice smooth cam action that happens. The results are very repeatable. Um, the you're really ensuring accuracy and definite torque delivery with the CamOver style of tool. Again, these are part of the ISO 6789 uh, classification of tools. But again, when it comes down to the mechanisms, that's going to make the difference as it relates to the tool itself. So if we take a look at how this differs from the previous two that we looked at, let's take a look at this particular animation. So if we take a look at the cam mechanism on the FG screwdrivers, we have the cam as it rotates will push the spring housing ball bearings into the spring housing, which then push on a larger ball bearing, which compresses our spring and gives us our torque value. So we get a very smooth action as it relates to the tool camming. So let's go ahead and take one more look at this so you get a real good idea. The cam will rotate, push in on the spring housing ball bearings. Those ball bearings then push onto a larger ball bearing, and that will compress the spring, giving us our smooth cam torque action. So a much different design than you would see with the other two that we looked at. So now let's move on to torque wrenches. Again, there are a number of different styles of torque wrenches that are in use. We have click style wrenches. We have beam style wrenches. There are electronic wrenches. There's also breakover style wrenches. And then we also have split beam style of wrenches as well. And all of these wrenches do very well as it relates to being able to signal that torque has been achieved. The one thing that they do not do very well is helping to prevent the operator from adding additional torque to the process. And so if we take a look at one wrench, which is the most popular wrench that's being used, is the click wrench. Now, if we take a look at the click wrench and how it works within its way on signaling torque, for the most part, a lot of the wrenches work in this particular fashion. So we have our spring, we have our head mechanism, and then we also have what is called the pivot block. And so as torque is being applied to the wrench, the spring gets compressed, and at one particular moment, the pivot block is going to, well, pivot. And this is what causes the click within the click wrench. So we do have that signal that torque has been achieved. However, the wrench has about 3 degrees of deflection before we have, before we start adding additional over torque to the wrench. So as the operator pulls it, the pivot block will click. Then it is up to the operator to stop pulling on the wrench, or else they're adding additional over torque. And that is a very fine line between once the click happens and once the operator stops pulling. So here's an animation to demonstrate what we were talking about. So as the wrench is being used, the click happens, and if the operator does not stop pulling on it, we'll see additional over torque for the click wrench. Now this is what it would look like in a graph form. As we apply load to the wrench, we hit our target torque, which is going to be the click. The wrench will then deflect. And if we don't stop pulling, again, we're adding additional over torque to that assembly. So let's take a look at the CamOver Style tool. Now you may notice that there is not a scale on this tool. That is because the tool is set internally. There is a torque adjustment mechanism, so the wrenches are preset. There's an end cap that's put on this tool to secure it, to make it tamper-proof from the operator. So unlike an adjustable style click wrench, there's not the opportunity for an error to be made with an accidental adjustment to the tool, as many click wrenches use the handle for the adjustment. So here's the animation of how this works. Again, as the wrench, we use it, the cam will go ahead and push the follower, compress the spring. Once the spring has been fully compressed, the follower then will just move into the next cam lobe, and we can go ahead and repeat the process of the torque delivery. So we can come to an application, and if you try to use that same fastening on that one fastener, you're always going to run up to the target torque. Then the tool is going to slip. And again, you would always be reaching the target torque, and you'll never have the opportunity to introduce any type of over torque to your application. So in very critical type of applications, it's very important to be able to control the final torque result. With that, we can do it with the CamOver Style of tool. So here's a video that we have just recently put out on using the click versus cam. And again, this is, as I mentioned, with the different modes, we can go ahead and we can see where the wrench clicks and any type of over torque value within that torque reading. And so if you notice, the click torque on the wrench is extremely very, very accurate. However, just with normal use, you can see we're adding nearly a third of the torque that we are trying to achieve at our 30 Newton meter setting. And so our CamOver tool is set to around 31 Newton meters. And you can see on the analyzer that we aren't seeing any over torque. So this is going to be our final peak torque that we are seeing on the CamOver Style tool. So again, this particular tool gives us the ability to have it be non-operator dependent. It's also very easy for the operator to be sure. It's a non-length dependent style of tool. The moment or the fulcrum point is at the end of the tool, so we can hold it anywhere up and down the handle. We're not going to see any changes in the torque delivery system. Unlike a click wrench, as our pivot block is in the side of the wrench, that changes our fulcrum point there. So if an extension is used, or if the hand is moved up the handle, instead of using it where it's designed, that's going to give us, again, different torque values than what we're trying to achieve. So this is how we can really make sure that for critical type of applications that we're utilizing the CamOver Style of tool to make sure we get a nice, smooth, and accurate without the possibility of introducing any over torque to the application. So at this time, we're going to ask if there's any questions, and we can go ahead and go through those questions that you might have. So Casey, are you curating the questions today?
I certainly can. Ooh, let me. All right, can you guys hear me now? Sorry about that. All right, Dave. So the first question is from Raina. She is asking, do these tools function for medium volume production? What are the disadvantages or advantages?
For medium production, certainly they can be used. Um, the One of the obviously the big advantage of these particular styles of tools is that you're guaranteed to get the torque that you're desiring without any type of over torque with that particular. So once the wrench cams, the operator knows that they've reached the torque value. Some of the disadvantages may be that you may have multiple types of torque settings within that application. So there may be the need to have different tools set at different torque values. And that would be something that may be a disadvantage. The fact that the tools can ultimately be used again by any operator is going to be a big advantage. Again, with a click style tool, if you have someone that is very fast, very aggressive, trying to make it through the production and not taking care to be able to use the wrench properly, then you may see a tremendous amount of over torque with that. And again, that would be a big disadvantage. And this is really very, very evident the lower in torque that you go. So with a very low torque wrench that you might be using in inch pounds or in the low foot pounds, again, that ability to add additional over torque is very, very easy to do with a click style wrench or even a beam wrench, and very possible with an electronic style of wrench as well. Again, all of these wrenches, they will signal when torque is achieved, but you will never be able to prevent the operator from adding additional torque to your fastener. And adding more torque is not better, as the saying is, the tighter the better. That is really going to put a tremendous amount of stress on the fastener itself. If you move it, especially into its elasticity, and you move it out of that plastic state, then you're going to have the ability for that bolt to fail. So,
All right. The next part of that question is, does this wrench require calibration?
it does require calibration. So it is part of the ISO 6789 classification, which means that it should be calibrated every 5,000 cycles. So that is the calibration cycle for this classification of tool. We do have tools in our CamOver series that have been set once, have gone back through their calibration process and haven't had the ability to be adjusted. And you can go into the the tens of thousands of cycles before any type of adjustment might be needed. But the classification for those tools is every 5,000 cycles. They should be calibrated. But if they're checked with an analyzer on a periodic basis, then the traceability to that analyzer then becomes how that particular tool can still remain in its calibrated state. That's another webinar, but
All right. And then we have a question from Ben. Will these preset CamOver wrenches come in time as an adjustable wrench as well?
they will. We should see those on the horizon very soon.
All right. That is all the questions I have in the chat. If anybody wants to add anything last minute, go ahead and add that now. Other than that, that's it, Dave.
All right. Thanks again for visiting with us today. We hope you have a great rest of your day. Have a good holiday next week, and we'll see you on our next webinar in December. Thanks so much. Have a good day.